Imagine you have a wire exactly 50 inches long, notched at every inch. If you can only bend it at these whole number marks, how many unique, complete triangles can you create? Listing every set of 3 numbers that adds up to 50 is one approach, but finding the exact count requires a filter for the sets that actually close. This shows why a simple sum isn't enough. If we notch our wire into lengths of 5, 20, and 25, the 5 and 20-inch segments can't reach far enough to touch. They fall completely flat against the 25-inch base. For a triangle to physically close, the 2 shorter sides, x and y, must combine to be strictly greater than the longest side, z. When we adjust the lengths to 16, 17, and 17, the sum of the short sides is 33, more than enough to meet at an apex. This physical requirement, that the sides must reach one another, transforms a broad counting problem into a focused search with clear boundaries. Before we count, we have to eliminate duplicates. A triangle with sides of 10, 18, and 22 inches is the same shape as one with sides of 22, 10, and 18. Rearranging the order doesn't create a new shape, it simply rotates it. To ensure we count each unique triangle once, list lengths from shortest to longest. X is less than or equal to Y, which is less than or equal to Z. Enforcing this order ensures every unique triangle appears exactly once in our list. Now we can find our search area. Since Z is the longest side, we need its maximum possible length before the triangle collapses. Our perimeter is 50, so the shorter sides equal 50 minus Z. Substituting this into our inequality gives 50 minus Z is greater than Z. This simplifies to Z being less than 25. Using whole inch marks, the maximum longest side is 24. Knowing Z cannot exceed 24 gives us a hard ceiling for our count. We also need a floor. What is the smallest possible value the longest side can have? If Z is the largest side, the perimeter cannot exceed 3Z, like in an equilateral triangle. Dividing 50 by 3 gives 16.66, meaning the longest side must be at least 17. Our search for Z is narrowed to the 17 to 24 range. Try applying this framework. If we set Z to its maximum of 24, how many valid whole number combinations for X and Y satisfy our rules? By defining both the floor and the ceiling, we ensure that the list of combinations we find will be exhaustive. When Z is 24, the 2 shorter sides must add up to 26. Following our ordering rule, we find exactly 12 valid pairs, starting from 2 and 24 up to 13 and 13. Applying this to the rest of our range reveals a steady pattern. As the longest side gets shorter, the number of valid configurations shrinks until we reach just one possibility for Z equals 17. Adding these counts together gives our final answer. A 50-inch wire forms 52 unique whole number triangles. The systematic approach turns the search for these 52 distinct triangles into an organized tally. This process isn't limited to a 50-inch wire. The same 4 steps work for any length. First, order the sides to prevent duplicates. Second, find the upper bound by dividing the perimeter by 2. Third, find the lower bound by dividing by 3. Finally, count the pairs within that range. Defining these logical boundaries allows for a clear path through a problem that otherwise feels like an endless list of possibilities.